Okay, so here I want to show you the law of large numbers and what that means. Okay, so the law of large numbers means when you have this average random variable, okay, you're taking an average of n items from a distribution. It could be actually any distribution. It's going to approach mu, which is the actual population mean for that distribution for all items possible. Okay? So this only is going to happen when n approaches infinity. So as the sample size, when you're taking more and more items from the population, the average of that random variable is going to approach the expectation of that. So the average value of that is going to approach mu. Okay? But this only holds true if we assume that x1, x2, all the way to xn, so those are the n random variables, are IID, which means independently identically distributed. So they're all coming from the same distribution. They're all identical, okay, which means they all have the same mean. We'll call that mu. And they have the same variance, which we'll call sigma squared. Okay, so xn bar is we're going to call the average random variable. Okay, so now what we're going to do is, to show this, we're going to take the expectation of xn bar. The expectation means the average of it. Okay, the expected value of what we expect this to be. Okay, so now expectation is linear. And the expectation of when you have a constant, you could pull that out in front. So over here, we have, this is 1, n on the bottom is 1 over n. That's a constant. We could pull that out as 1 over n times the expectation, okay, of this sum of the n random variables. Sorry, expectation, x1 plus all the way down to xn. Okay, now, right, well, like I said, the expectation of a linear combination is linear. So you could take the this will actually equal 1 over n times the expectation of each one. Down to xn. And since all the random variables are the same, they all have the same mean, which is mu. Okay, so we could write this as, okay, now we have n of them with the same mean, so that's n mu times 1 over n. Okay, and the n's are going to cancel out. Just in parentheses. Okay, and that's going to leave us with mu. So that's always true in general. For any average random variable, when you take its expectation of a bunch of an average of random variables, so you're adding, this is the average, we're adding n random variables, so that's why we're dividing by n. That's the formula for average. It's always going to be equal to the actual mean of the actual distribution. Okay, here is we want to figure out the variance of this average random variable. So again, this is the formula. We're adding n random variables, and we divide by n. So now here's a formula in general. When you want to take the variance of a constant, let's say c times x. X is a random variable, c is a constant. This is going to always equal c squared times variance of x. Okay, so this would be useful calculating this over here. So 1 over n is a constant. So let me just erase this over here. Okay, So we could pull out the 1 over n, pull it out, but we have to square that. So over here, we're going to get 1 over n squared times the variance of this sum. Okay. Now, since these are all independent random variables, the covariance between any random variables that are different is going to be 0. And the covariance between itself is equal to the variance of itself. So all of this is going to come out to be equal to 1 over n squared. Okay, so when all n random variables are IID, or independent, you actually could take the variance of each one separately, just like we did for expectation. So we're going to get variance of x1 plus variance of x2 plus variance of xn. Okay, so normally when you're taking a variance, you usually have some covariance terms, but all of those are going to equal 0 because each random variable is independent. Okay? And now the variance of each one are all the same. They're all sigma squared. So we're going to get 1 over n squared times, okay, we have n random variables, n of them, times sigma squared. Okay, the n's are going to cancel out. Sorry, one n will cancel out with one of these n's, and you're left with sigma squared over n. Okay, this is going to be the variance of xn bar, sigma squared over n. Okay. So now what we're trying to do is saying as n goes to infinity. Okay, so let me erase some of this. So let's look at this. As n goes to infinity, we'll take the limit of this sigma squared over n. Okay, so since n is on the denominator, when n becomes very large, sigma squared, which is a constant over basically going to infinity, this is going to approach 0. Okay, this limit is approaching 0, which is going to tell us that when you're taking average of n random variables, as the number of variables gets more and more and more and more, so the larger sample you're taking more and more and more, this is called a sampling distribution. It doesn't matter which sample you take. Between every sample that you're taking, there's going to be the variance. This means the variability among samples will be 0, which is telling you that every sample is basically going to become almost the same sample. There's almost no difference between when n goes to infinity. And the expected value of every sample is mu, which means that pretty much every sample is going to be mu. There's going to be no difference between every one. There's no variability. Okay, so let me write that down. Zero as n goes to infinity. Okay. Now this makes sense because when the sample size is so big, when n is so big, you're almost like taking almost every element in the actual population. So no matter what sample you take, if you're taking such a large sample, it's almost like every time you'll be taking the same sample anyways. Okay, so the variability will be 0. You're going to expect the average of those values to be the actual average in the population. And that's the law of large numbers. So when you're taking a very large group of values, your expected value you're expecting is to be mu, and you're almost expecting the variability to be approached 0. So, okay, thank you.